Hello, I'm Dr. Brian Fraser. I'm a senior lecturer in the Department of Computing Science at Simon Fraser University, and today I'll be talking to you about the software systems program that we offer. So, to start with, why do we like computing science? So normally I'd be giving this talk to a room full of people, you in person, and you'd be able to answer what it is that interested you in computing science. Of course, you're not here in my room, so perhaps I'll just start by telling you what it is that interested me in computing science. To me, I was always interested in the power of computers and the things you could do with them. You could give them instructions and have them do what you told them to do. And then realizing that I could use that tool to start to really make a difference and solve problems. First, start off with very simple problems, of course, but you then start to realize, well, hey, I can start to solve bigger and bigger problems and make a real difference in the world with, applying these solutions. So whatever it is that brings you to computing science, I hope that we're able to help you on that journey. So, well, some people would say, well, I like computing because of the money. Yes, indeed. There's a great possibility to be paid to do what you've learned to do. And I'll say that there's one thing I'd change on that. It's paid to do what you love to do. If you come into computing loving computing, then it's fantastic because there's a lot of opportunities out there. Great prospects both locally and of course internationally. Your skills are just transferable anywhere around the world. You stay up to date with things and you can work on huge numbers of different projects. My quick Google foo gave me a guesstimate of $70,000 or $85,000 for a salary in BC, in Vancouver area. This of course isn't the starting salary, but for I think it was software engineering through one website. But anyway, regardless of the exact number, it's still, you can make really good money doing something you love to do, which is fantastic. So what can you do in computing science? Well, one big thing we'd say we could do is solve problems. So there's some standard ones you might be able to do, like an autonomous vehicle. You might be able to do genome research. Of course, genome research is very important at the moment with the coronavirus and with the things we can learn about that. Some cool things that we can do, actually have done inside the software systems program is, first off, a maternal health referral program. So about a year ago I started working with a group of doctors who do work in a Ugandan refugee settlement, and they needed a way to track referrals. When somebody was saying, okay, here they've got a great tool for diagnosing when an expectant mom has some health issues that need to be sent off for more tests or further help, and the referral system at the moment was just a piece of paper, and that paper was almost always lost. There was no feedback to the initial person who may have referred the woman as to what follow-up treatment might have been required. And so we developed an Android app that would allow us to send via text message a quick kind of like, hey, we're expecting someone to come in, here's the information about the initial reading. And this is fantastic because we're actually able to take this, and in the fall, so in 2019 in the fall, we were able to have groups of third-year students take this project and run with it and build a server-side component so that our Android app would talk to the server-side component, put that in. A doctor that's at the hospital could be looking at the waiting room and go, okay, well, do I expect any other patients to come in? So she could pull up the listing and say, oh, hey, we've got some referrals of people coming in. Did they actually come in or not? And then when the doctor provides some treatment to the patient, that information could be passed back to the initial person who diagnosed them and say, here's some follow-up treatment for what you can do to help look after this woman going forward. So this is a really valuable tool, and what's fantastic is that it could save lives. Really, really save lives. And students in third year were able to implement this system. So that's a lot of value, not just to companies, $85,000 possibly to local companies, but saving lives in the world is making a huge difference. Another project I worked on previously, this was for a second year software engineering project, worked with a company that worked out of Ghana, and they could do surveys to find out what people were thinking on certain issues about, would you rather pay more for electricity and have it more stable, or would you have electricity be cheaper and less stable? And those are sorts of questions they needed widespread input from. And it turns out that a lot of people have cell phones all over the world. So they're able to use cell phones to deliver these surveys to many, many users. And so students in 276 were able to build an Android application that could allow the average person to take a survey, or even someone working in the field to create a survey, which has a great global reach. So what is it that we do teach in software systems? What do you get? Well, first off, software systems is fundamentally about software engineering. That's our focus. So I like to run an analogy. So imagine, or an example, imagine the next person walks into your room, says, I have $30 million, and I'll give it to you and whoever you work with to design the next control software for SkyTrain. Now, the control software for SkyTrain is pretty complex. It's life critical. There's a lot to it, a lot of testing, probably a lot of maintenance down the line as they add new systems online. So this is a very complex piece of software. What do we need to make that happen? Because I wouldn't mind having part of that $30 million like you would. So we're going to need great code and smart algorithms. And that's what you'll get everywhere. You take a reputable comp sci program and you'll be taught great coding and smart algorithms. Now, great coding, maybe not everyone gets that because we teach them how to code, but maybe we don't teach them the best way to code. So we do focus on that too. Other things that we bring in are things like teamwork. So we force students to work in teams because you'll have to work in teams later on. We'll look at collaboration tools and getting a competent grasp of using those, plus also even understanding the hardware. To turn on the brakes, how do you do that with the SkyTrain? So we have a course that talks about that. I'll mention that in a moment. So a great example of what we might teach in, say, second year would be a course on object-oriented design. This course is in Java, but the language is almost immaterial. The idea of what it is you're learning is the skills to do high-quality object-oriented design, and you want to look at not just having your code work, because anybody, any fool can get the compiler to like your code, but your code should be great code so that other human beings like it and want to read your code. So I might give an example here. If you've done a little bit of coding already, that's great. You'll understand kind of what's going on here. I think I might have made up the language. Anyway, on the left here we got a function named foo, which is the classic name for a generic computing science function. But what does that tell me it does? Nothing. It could be anything. I've got some variable names like cn, and I print out c, and I don't really know what it's doing. And furthermore, it's a complete mess. On the right, it's named print sum 1 to 10. Well, even without reading the code, you can probably guess what this is going to do. And then my variables are named clearly, the structure is very clear. Fundamentally, this is the kind of code I could maintain, and I could figure out what it's going to do without having to slog through the details. So this code is way better. And this is just, what, 10 lines of code? Imagine you had 1,000 lines of code, or 20,000 lines of code. How much could you do? How could you make it really, really great? And so Compute 213 is a course where we do look into that kind of issue. Getting into third year, this is a group project course, Compute 373. It's called Software Development Methods. We put teams in groups of about 8 students, and we give them a big project, semester-long project they have to go through, multiple iterations, so they learn agile development, and they learn the real value is that the things that you do wrong in the first iteration, you kind of have to live with or fix throughout the rest of the iterations. And that's very powerful because then you realize that the things I do have meaning and I need to do it right. So in fact, this is one of the courses where we work with a customer sometimes. When I teach the course, I try to find a local nonprofit, or in this case, an international nonprofit. And this is the course where the students implemented the system to do the healthcare referrals. And the customer actually loved them. All the projects came out really, really great. And one project was selected for continued work, and we're hoping to actually be able to deploy it in the field sometime soon for field trials. Another course is in fourth year. This is a course I teach on embedded systems. We use a board called the BeagleBone Green. It's kind of like the Raspberry Pi, if you've heard of it. This has some other benefits that I like. And on the bottom is the standard BeagleBone Green, and on the top we put on what we call the ZenCape. And it's got a whole bunch of peripherals that allow us to do other interesting things. So for example, it's got audio and a few things. One great assignment I love in this course is they call the air drummer. And so you've all kind of, sat in your car and pretended you're drumming. Well, this, when you do it and it's plugged in, you can make it actually play sounds like as you move it in a different direction. And how we do that is with an accelerometer. So it's running embedded Linux, and you're interfacing with low-level hardware to read what's really going on with the system. You're displaying it on a 2-digit 14-segment display. You're in real time generating the PCM encoded audio to play out of the speaker here. And so you get a feel for the low-level stuff, you get a feel for operating system level stuff, and even some web stuff. So we've got the board at the same time produces a web interface that you can control it from your standard browser. What is software systems compared to the computing science major? So in Burnaby is where we teach the computing science major predominantly, and both of these programs are within the School of Computing Science, and both will give you the skills you need to be a software developer. With software systems, we specifically focus on a few things. We talk about applied skills, so we try to do a lot of hands-on courses, a lot of things where you actually are in there and doing the code, writing the code, a lot of that. We talk teaching teamwork, so we're forced to work in a team and get that experience. How do we work through issues, and how do we kind of have good, solid teamwork skills when we graduate? And then looking for good quality software design, coding standards, coding style, things like doing a code review. How can you look at someone else's code and then give them feedback on how to improve? And when someone does that to your code, how can you take that feedback and really take it to heart and get better and better? So that being said, you can't focus on everything. So we do focus less on some of the theoretical aspects, perhaps, and also we don't require students to take things like databases or graphics or artificial intelligence. But that being said, there's room with electives to take many of those different courses. So if you take software systems, we will force you to take courses like the ones I have mentioned, where you must learn to do object-oriented design and how to do it well. And you must learn how to do a large team experience. So that's part of sort of what's built into the program. The program is largely offered through the Surrey campus. This is in the new Sustainable Energy Engineering building. It's a fantastic new facility, state-of-the-art equipment inside. So some of the advantages that we've got in Surrey, we've got smaller classrooms in the software systems courses usually, so smaller classes. It gives you kind of a cohort feeling because you tend to progress through the program with many of the other students. There's quite a bit of flexibility there, but you still end up knowing quite a few people in your classes. As an example, we're looking at the second course in first year computing science, so the course you'd be taking in the spring. And at Surrey, we're offering Compute 135, and there were 82, I think, students in it this semester. And in Burnaby, a course like Compute 125, which holds the same sort of place in the curriculum, I think there were 198 students or something like that in it this past semester. So quite a different feeling. Now, 80 is still a lot of students, but you can still kind of get to know a lot of people in that setting. Also in Surrey, we've got quite a few study rooms, modern facilities. There's a food court in the mall, which is adjacent to the Sustainable Energy Engineering building, of course the shops. And a great feature is SkyTrain. It's a 2-minute walk from SkyTrain into the Sustainable Energy Engineering building. And so if you're in Surrey, it's great, it's in Surrey, you don't have to cross a bridge. If you're in Burnaby or Vancouver or easy access to SkyTrain, it's really convenient to get into the Surrey campus, maybe even faster than getting to the Burnaby campus sometimes. So that's all I wanted to say today. Thank you very much for joining us here. I'll be teaching Compute 130 in the fall of 2020, so if you're enrolling then, I look forward to meeting you then. I look forward to kind of seeing the great things that you'll accomplish throughout your degree. Thank you very much.